Unit 3, which focused on the theme of weather, contained 2 chapters. We covered chapters 10 and 11 here. So we're going to go over chapter 10 first, but before we do that, we will just give an overview. I'll review the sort of thematic aspects of the chapters that we looked at here. Most of the weather phenomena you experience results from physical changes in matter. Differences in density cause the movement of air that you experience as wind. Heat from the sun causes water to evaporate and rise into the atmosphere. Water vapor is moved about the temperature and pressure differentials in the air, only to change phase again and become some sort of precipitation. To understand weather, you had to understand phase changes and the interplays of variables such as pressure, temperature, and density. In this unit, you studied patterns among weather variables. You also studied gas behavior and gas laws to help relate the behavior of air masses around Earth to the prediction of weather phenomena. Chapter 10 was called Physically Changing Matter. It was where we were introduced to some of the weather terms and what it meant for a change to be considered physical. Really what it meant for a physical change to occur. The first thing we did was we just introduced ourselves and we got familiar with some of the weather variables, things we would find on a weather map. Cold fronts, warm fronts, high pressure, low pressure, precipitation, clouds, temperature, jet stream, and the relationship between those different variables. We looked briefly at physical changes, specifically phase changes of matter, so going from solid to liquid to gas and what each of those are called. There are 6 of them, and you should be familiar with what their names are and between what phases they are going to and from. We looked at proportional relationships, and this was our introduction to gas laws, really. We did quite a bit of work with proportional relationships to understand what it means for a relationship to be proportional when we have data. And we understood that if we plotted data, we could know if the relationship is proportional, like this one here, if it was a linear, if it was a straight line that went through the origin, 0, 0. But in this relationship, we have data that's linear, but it doesn't go through 0, 0. So we cannot call this relationship a proportional relationship. Now, what that really means to you, you're familiar with using a proportion as a mathematical or algebraic tool to help you solve problems. Well, you can only use a proportion with data that's proportional, right? So if I have data that's not proportional, using a proportion to help me find an unknown, I'm going to get a number. It's not going to be the right one if the data is not proportional. Now, looking at the data here, the sample data between carpet and cost, what it means if I'm looking at data, calling the data proportional, is that the data in the X column is related to the data in the Y column by a common factor, right, that you're either multiplying or dividing by. But it's going to be the same number, which we called a proportionality constant. So here in this example, the cost in dollars per square feet of carpet, 10 square feet of carpet is equivalent to $15. 20 square feet of carpet is equivalent to $30, and 50 square feet is equivalent to $75. So the constant here is 1.5. That is, how do I get from square feet of carpet to dollars? In each case, I'm multiplying by 1.5. Because I'm multiplying by the same number to go from X to Y, that data is proportional. And if we think about extrapolating this data set, 0, 0 is a point here. Because if I had 0 square feet of carpet, it's going to be $0, right, in cost. So it's important that 0, 0 needs to be included in the data set if we are calling the data set proportional. We were introduced to proportional relationships by looking at how water would fill up a container. Specifically, we used a rain gauge, and we saw that any container that had parallel walls, the volume of water that filled the container versus the height of water, right, measured in centimeters or inches, would be proportional. But in something like a flask, an Erlenmeyer flask, or a Florence flask like we used in class, the round bottom flask, the height versus volume would not be proportional. Because even if you put in 2 milliliters of water every time, because you don't have parallel walls, the water's height would not increase by the same ratio. We then applied that idea of a proportional relationship to density. And we've seen density before in this course, and specifically in Unit 1. Density is equal to mass over volume. Now, if we think about that relationship, mass over volume is going to get me a common number for a substance at a given temperature. So density is a constant of sorts. It is the constant that relates the mass of a substance to the volume of a substance. Just go from mass to volume or volume to mass. The constant that links those two is density. Again, thinking about what it means for the data to be proportional, if I have zero mass, I'm going to have zero volume and vice versa. So 0, 0 fits on that data set as well. We then worked off of this idea with density that if we have one phase of a substance and it changes phase, something is going to stay constant, but something is going to change. And what is going to stay constant is the mass, right? One thing we have sort of been emphasizing heavily this entire course is the idea of conservation of mass, conservation of matter. And what it means for matter to be conserved is that in any sort of change, I'm starting with a given number of atoms of an element, and I'm going to end with those same number of atoms of an element. They may, if it's chemical, unbond, rearrange, rebond. If it's physical, like we focused on in this chapter, they're going to move further apart or closer together, but the number of total atoms will be the same, and the mass is coming from the mass of each individual atom. So if that's the case, the mass before is going to be equal to the mass after. Now we can see this in this picture here. This is 1 gram of snow. Now, that 1 gram of snow is representing the mass. The volume given by the graduated cylinder there is telling me that it's about 4 milliliters. Now, when that 1 gram of snow melts into liquid water, I'm still going to have 1 gram of water because the number of water molecules here is going to be the same here. The only difference is here, this is the volume that matter is now taking up. Because when water melts, those molecules get closer to each other. I have the same number of them, but they're just moving closer together, so they are taking up less space, which is why the volume changes from 4 milliliters to 1. Now, one thing we looked at with water specifically is that water molecules arrange themselves in the liquid and solid form, unlike any other substance. Every other substance, when it goes from solid to liquid, the particles actually expand just a little bit. But water molecules are different. Water molecules take up much more space when they are a solid. You can see the image here. We've seen this image many times throughout the year. They form that hexagonal arrangement with the big open gaps, right? That's why ice takes up more space than liquid water. That's why, because it takes up more space, it's less dense. That's why ice floats on liquid water. When water turns into a liquid, the particles actually get a little bit closer together, and that's different than most other substances. But even though the particles are just moving further apart or closer together, the number of water molecules are staying the same, so the mass is going to be the same. Now, one thing we have to consider, if we have, let's say, 50 grams of ice, and we want to figure out how much water we're going to have, well, I'm going to have 50 grams of liquid H2O, but the volume is going to be different. The volume of ice, we're going to have to figure out using the density of ice, which is 0.92 grams per milliliter. And if I know that this is going to turn into 50 grams of liquid water because the mass is going to be the same, then I can figure out the volume of liquid water by using the density of liquid water, which is 1.0 grams per milliliter. So remember, we looked at problems where if I'm starting with a certain volume of a substance and it's changing phase, the volume is going to change, but the link that's going to help me determine how the volume is going to change is the mass, because the mass is staying constant. So that will be my link between the different phases, and then I can use the density of the different phases to figure out what the new volume will be. We looked at an introduction to thermometers and how they work. Briefly, we constructed our own, and we saw what it took to come up with a scale. We needed a couple of set points on the thermometer to make a scale, and we saw that we could choose our own numbers, pick a different unit. That's how any temperature scale is created. Generally, how it works is you fill the thermometer, the glass tube with a substance that expands when heated and contracts when cooled. So water would not be a good option for that because it does the opposite, right? But something like mercury or ethyl alcohol, which are commonly used in thermometers, would be a good fit. The particles expand themselves as the temperature increases, and they contract as the temperature decreases. And that's how we measure temperature, right? There are 3 temperature scales that we focused on in class: Fahrenheit, Celsius, and Kelvin. You should be familiar with all of them and the conversions between each of them. So we looked first at the conversion between Fahrenheit and Celsius, and I'm going to go below here to fill them in. So degrees Fahrenheit, we take our Celsius temperature, we multiply it by 1.8, and we add 32. And then we looked at the conversion from Celsius to Kelvin, and really Celsius to Kelvin was just adding 273 to the Celsius scale. That is reflected in the graphs. Remember, we looked at the graph of gas volume versus temperature before we looked at Charles's law to show how this, while it's linear, is not proportional because it doesn't go through 0, 0. So if we take this Celsius scale and we move it, we shift it 273 units so that it now goes through the origin, that is essentially how we get the Kelvin scale. We take the Celsius scale and we shift it 203 units up so that it goes through 0, 0, and that's where we get that conversion from. This scale is, as we've seen, very beneficial for when we're doing math because we can set up a proportion. If we have a gas volume and a temperature and then we're changing the temperature and want to find what the new volume is, because this data is proportional, we can set up a nice simple proportion to solve it. If we were using Celsius, we'd have much more complicated equations to deal with. We introduced ourselves to the molecular motion of gases, the idea that in the kinetic molecular theory, it says a couple of things about gas molecules. They're in constant random straight line motion. They're all moving with different speeds. So we describe the speed of a gas sample as the average speed or average kinetic energy. Because if they're all moving with different speeds, then we can't say that, this sample is moving with X speed or Y speed. So we describe it as an average. Some are moving fast, some are moving slow. They are all making collisions with each other and with the walls of the container. That's the only time they'll change direction. And if we increase the temperature, we provide them with more heat energy. They will start to speed up, and if we take heat energy or we cool them down, the average speed or average kinetic energy will decrease and they'll start to slow down and contract and come closer together. So that was our basis for the first gas law that we were introduced to, which was Charles's law. And Charles's law related the Kelvin temperature of a gas to its volume. The idea that if you increase the temperature of a gas in a flexible container, right, that's the caveat, it has to be a flexible container because for the volume to change, the container has to allow for expansion and contraction. In a rigid container, we saw some other gas laws observed, so this one we're dealing with a flexible container. The particles, if they absorb heat, will have more energy. They will move faster and further apart, and therefore increasing the volume. And if we decrease the temperature, the particles slow down and contract. They'll start to move closer together. Those intermolecular forces start to strengthen again, and the volume will decrease. The graph for Charles's law looks just like the proportional, the direct proportion, right? Direct proportion means that one variable increases as the other increases, or one decreases as the other decreases, right, by a constant ratio. And here there are a couple of diagrams just to illustrate Charles's law conceptually, right? Boiling water, the particles are going to move faster if we have that balloon in boiling water, so that's why the balloon is bigger there. If we decrease the temperature, putting that balloon into ice water, the particles are going to slow down and come together. Remember, it's a direct proportion. So if you look at the math here, and we have nice numbers to make it simple, we are starting with 0.5 liters of a gas at 200 Kelvin, and if we increase the temperature to 400 Kelvin, then the volume is going to, number one, increase because we're increasing the temperature. But because we're increasing the temperature by a factor of 2, and because it's a direct proportion, then the volume's also going to increase by a factor of 2, right? That common factor that relates the two. So it's going to go from 0.5 to 1 liter, right? The most important thing here is that you have to use Kelvin temperature because Kelvin is the only temperature scale that's proportional to gas volume. And we're using a proportion, right? So if we're going to set it up as a proportion, we need a temperature scale that's proportional to gas volume. So let's try one example here. Miss Rodriguez inflates a balloon for a party. She is in an air-conditioned room at 27 degrees Celsius, and the balloon has a volume of 4 liters. Because she is a curious and intrepid chemistry teacher, she heats the balloon to a temperature of 57 degrees Celsius. What is the new volume of the balloon if the pressure remains constant? So they don't mention, in fact, they mention pressure is remaining constant. So that is my key for that this is going to be observing Charles's law, right? Volume and temperature are changing. I know the relationship is direct between them. So I'm setting up my formula like this in a direct relationship. We divide the variables to get our proportionality constant. The red flag should have gone up with the Celsius temperatures that are here. So we have to convert these to Kelvin by adding 273. We'll do that here. And then what we're going to do is just plug in our numbers here. So we're starting when the volume of the balloon is 4 liters, the temperature is 300. So we want to make sure that those variables that are linked go on the same side. And we want to figure out what the volume is going to change to when the temperature is increased to 330 Kelvin. We can cross multiply. We're going to get 300 Kelvin times V2 is equal to 4 liters times 330 Kelvin. And then once we do our algebra, we should get that the volume changes to 4.4. That matches our prediction because we should have predicted the volume was going to increase when the temperature increases. And the temperature only increased by 30 Kelvin, so the volume should not increase by that much. Remember, it's changing by the same factor. The last thing that we looked at in this chapter was relating the idea of how temperature affects the volume of a gas and how that's related to cold and warm fronts. And then just the cycle of how air moves in the atmosphere. So a cold front is when you have cold air that's overtaking an area, and a warm front is when you have warm air that's overtaking an area. Remember that the idea of warm and cool is relative. So when we think of warm, we think of like a 90-degree summer day. When we think of cold, we think of a really frigid, 2-degree winter day. It's relative. So cold and warm can be whatever temperature they want to be. It's relative to the area that they're moving into. Whenever we have a warm front moving in or a cold front moving in, we're always going to have cloud formation. We're always going to have clouds form. And where there's clouds, there's precipitation. A cold front here, right? You have warm air on the ground already. Cold air is moving in. So again, temperature doesn't matter. It's relative. Cold front means that the air that's moving in is just at a lower temperature than the air that is already there. So we have this cold air moving in that direction. The cold air, we know from Charles's law, is going to be more dense than the warm air, because if the gas molecules are cooler, their particles are closer together. Closer together means that it's more dense. The cold air is going to sink down and have to push up this warm air that was already there. And we get, as a result of that, the cloud formation to form directly in front of the cold front, right at the point where the cold front and the warm front meet. The clouds tend to be bigger, and you get to have more heavy precipitation in a shorter span, right? Shorter sort of area. And this will last for a shorter period of time. Now, when a warm front comes in, that means you already have air on the ground at a lower temperature than the air that's moving in. The air that's moving in is at a higher temperature. And because in warm air, the particles are more spread out because they're moving a little bit faster, right? Weaker IMFs. That warm air is going to be less dense. So the warm air is just going to sort of glide over the cold air that's already on the ground, right? Because the cold air is more dense, the warm air is less dense. So it's not going to sink down and push up like the cold air mass is going to do. And the resulting cloud formation that we get here is the clouds are going to form little by little as the warm air glides over that cold air, right? We get cloud formation in both of these cases because we have a change in temperature of the water vapor that's in the air. When we cool water vapor, we get it to go from gas to liquid, and the tiny little liquid droplets are what a cloud is. In both cases, this is happening. It's just how quickly is it happening, over what sort of land area is it happening, and how large the cloud's going to be or how thin are the clouds going to be. In the example where the warm front is coming in and the warm air is moving in, we get the clouds to form over a larger area. They're going to be thinner and more spread out as a result. And the precipitation that we're going to get here is going to be lighter, it's going to be steadier, and it's going to last for a longer period of time because the clouds are covering more land than in the first example above here with the cold front, right? Where the cloud sort of forms in one location. It's not over a lot of land. You get heavy rain because all of the water is concentrated in that one area to come down at once, where when the warm front moves in, you're going to get steady light precipitation over a period of usually several days. This diagram, which just shows a cycle of how the air masses heat up and cool down and the consequences of that. If air heats up, that means that the particles expand more, they're less dense. When they're less dense, they rise into the atmosphere. And as they rise into the atmosphere, eventually they're going to cool down. The upper atmosphere is cooler. So as they rise and start to cool down, the particles are going to slow down, come closer together, become more dense, and they will sink. And then as they sink, because the temperature increases as you get closer to the ground, will heat up again, start to speed up, spread out, and then become less dense, and we get this sort of cycle to happen over and over again. And it's up here that we get the clouds to form, right? We saw this also more in chapter 11, so we'll cover that in that review. But it's the process of the rising warm air that cools in the upper atmosphere, and that cooling of the water vapor, that gaseous water turns back into liquid water, undergoes condensation, and the accumulation of all those tiny liquid particles form a cloud, and once there's too many of them and they become too heavy, they will fall back down to Earth as precipitation. And that is where we ended chapter 10.